Dear students, in the previous class I have discussed about project risk management. In this lecture I am going to discuss about quantitative risk assessment methodology. Last class we discussed about project risk management. So, in this lecture I am going to discuss about quantitative risk assessment methodologies. So, the agenda for this lecture is the first quantitative technique for assessing the risk is failure mode and effect analysis. The second techniques which we are going to discuss today is decision tree analysis. The third method is simulation, especially we are going to use Monte-Carlo simulation to assess the project risk. Finally, I will discuss about what is sensitivity analysis and importance of sensitivity analysis for project risk management. The first technique is called failure mode and effect analysis. We shortly call it as FMEA. So, FMEA is the application of a scoring model. So, there will be 3 criteria. We will substitute or apply some value for each criteria, then we will multiply that, we will get a score for different type of risk. So, whichever is having the higher risk, that is most important risk that we have to focus on, or we have to mitigate that risk. So, it is a straightforward and extensively used, particularly in engineering, and easily applied to risk using 6 steps. So, in the failure mode and effect analysis, there are 6 steps that we will discuss. So, the step 1 and 2 is, the first step is list the possible ways a project might fail. If you take a project say Chandrayaan 2, so first they might have discussed that was failed, they might have discussed that what were the possible ways that project was failed, or if you are developing a new product, before launching the product you have to look at all possibilities of failure of that project, that is a step 1. Then we have to evaluate the severity of the impact of each type of failure on a 10-point scale. So, the second step is we have to assess the severity. So, how we are going to assess? If it is 1, it is no effect, severity is not that much. So, if it is a 10, it is very severe. So, based on the severity of that risk, so we have to assess the score for the term S. The third step is, for each cause of failure, estimate the likelihood of its occurrence L on a 10-point scale, where 1 is rarely occurs and 10 is almost certain. So, 1 represents, see look at this scale, likelihood is very less. So, 10 means the likelihood is more. The step 4 of failure mode effect analysis, estimate the inability to detect a failure, we call it as D, associated with each cause. So, we have to apply some score for this D. So, using a 10-point scale, if you are giving 1 means detectability is almost certain, so easily we can detect it, but if you are giving 10 means it is very difficult to detect that risk. So, 1 represents detectability is certain, 10 represents very difficult to detect. So, we discussed about 3 terms, one is S, severity, second is L, likelihood, the third one is D, detectability. So, find the risk priority number by multiplying these 3 terms, that is S, L, D. So, S represents severity, L represents likelihood and D represents detectability. So, we will get a score. So, then we have to consider ways to reduce S, L and D for each cause of failure with a significantly high RPN. RPN here is called risk priority number. Now, I have brought a sample table to explain how we got this risk priority number. For example, say there is a project 1, the first threat is tight schedule, like that we have 5 possible threat for the project. The second threat is cannot acquire the technical knowledge, third one is client changes scope, fourth is cost escalate, 5 is recession. So, we have for S and L and D we have supplied value. S means severity in the 1 to 10 scale. For example, with respect to severity, which threat is most severe threat? For example, this 8.5. cannot acquire technical knowledge, that is having highest score. So, with respect to likelihood, so which threat may occur, there is more chances to occur, that is the highest score. Then ability to detect, right. So, when you multiply this, we are getting a score, that score is called risk priority number. So, first we have to mitigate the risk which is having highest risk priority number, for example 170. So, as we see from the RPN number, risk priority number, the biggest threat are cannot acquire technical knowledge. Next to that is 160, that is client changes scope. So, first we have to try to mitigate these two risks. How we can mitigate? We can look for how can we reduce the severity. Then we can see the better methodology to predict, that is likelihood of that threat. Then we can develop a new methodology to detect that risk. So, the next tool is decision tree analysis. So far we discussed about failure mode and effect analysis, that is one of the quantitative techniques to measure the risk or to analyze the risk. The second methodology, quantitative methodology, is decision tree analysis. This tool is a simple in concept and especially useful for a situation where sequential event happen over time. So, whenever there is a sequence of events, then we have to assess the risk of that each sequential event, then this decision tree is very useful tool. For example, it would be appropriate to calculate the probability of getting one head or one tail in two tosses of a fair coin. For example, the picture here is, this is trial 1, this is trial 2. So, in the trial 1 there may be head or tail, in trial 2 here it may be head, here tail, or here may be head or here may be tail. So, the probability of getting a head on the first toss and a tail on the second toss can be found by using this decision tree. The probability of getting tail on the second toss also can be found using the decision tree. If we are only interested in probabilities, we call the tree as a probability tree, because our purpose is only to find the probability of getting some event on each trial. But there are some actions we are considering anywhere along the tree before the first probability event, say, or between the events, and we want to evaluate which actions would be the best, then it is called a decision tree. So, before each event, if we are intervening some action, then we want to know which is the best possible option. So, that can be found using this decision tree. Here our purpose is not to know the probability, to assess the consequences of each action. Now, I brought a sample decision tree analysis. So, here a company is looking for launching a vehicle, an automotive company. So, here the square represents the decision node, this is the decision node. The circle represents chance nodes. So, how to construct this decision tree analysis? So, suppose assume that automobile company has the three options to launch a new vehicle. For example, they can go for gas only model, say A1, or they can go for hybrid only A2, or they can go for gas and hybrid model. So, there are three options. So, we want to know the consequences or risk of these three options and which one we have to choose. So, suppose if the company goes for only gas only model, so there are three possibility. One is gas price increases, gas price may fluctuate, or gas price decrease. So, what we have to see? We have to see the consequences of this action if the gas price is increasing or decreasing or fluctuating. Similarly, if the company go for hybrid only, there are three possibility market condition. The gas price may increase or fluctuate or decrease. So, there is a probabilities attached to each chance event. There is a 50% chance gas price will increase. There is a 30% chance gas price fluctuates. There is a 20% chance the gas price decreases. Similarly, for third alternative, a company can go for manufacturing gas and hybrid models. In that case, the probability is, look at here, the probability is same for all these three actions, whether it is gas only or that is hybrid only or gas and hybrid only, because the market conditions of the price of the gas is independent of our actions. So, the first and the last, it represents the expected annual profit. What this 1200 means? Suppose if you go for gas only model, if the market, in the market the gas price increase, there is a 50% chance. So, there are two possibilities, go for gas only model, if the gas price increases, then the expected annual profit is $1200 million. So, like that it is 600. So, now if you see there is a loss here. What is the loss? If you are launching hybrid only vehicle, if the demand, if the gas prices decreases, there is a $200 million loss for you. But which is the best option? If you are an optimistic person, you will go for gas only model. So, there will be a $1200 million you can get as a payoff. So, this is a way of constructing the decision tree, but the calculation of the decision tree is done in the backward direction. So, first how we have to find out? We have to find out the expected monetary value of this action, that is a gas only model. So, what you have to do? You have to multiply this 1200 multiplied by 0.5 plus 600 multiplied by 0.3 plus 300 multiplied by 0.2. So, when you simplify, you will get expected monetary value for gas only model is 840. Similarly, if you go for hybrid only model, so here 1500 multiplied by 0.5 plus 300 multiplied by 0.3 minus 200 multiplied by 0.2, you will get expected monetary value is 800. Similarly, for third option, you will get expected monetary value is 650. So, we have to, the calculation should go in the backward direction. Now, we have to see which one is having the highest expected monetary value. For example, the first option, gas only model, is giving the highest monetary value. So, the suggestion, the recommendation for this automotive company is they should go for only manufacturing gas only model. So, they will get the expected monetary value in the sense average profit. So, average profit will be $840 million. So, this is the way the decision tree works. What is the point here? The construction of the decision tree is done left to right, but the calculation of the decision tree is done right to left. So, here square represents the decision node, circle represents the chance nodes, and the probability for all the alternative and corresponding chance node will be same. For example, 0.5, 0.3, 0.2. So, here also 0.5, 0.3, 0.2. The third option also 0.5, 0.3 and 0.2. So, this we will explain in detail. Now, we will come back to the some more basics on decision tree analysis. The figure illustrate such that a tree is solved one here, but a straightforward one with only one set of actions to choose from one set of events. However, it could be extended to multiple actions or events if desired very easily. So, a decision tree is created from left, but solved from right at the end with either decision node, as I told you, the square represents the decision node and the circle represents probability node. In the example shown, an automobile manufacturer is considering whether a new car model development project should consider only a gas, hybrid or both gas and hybrid model. In this example, three options are being considered. We have to choose, we have to recommend which one is the best option. So, there are three alternatives emanating from the decision node, each one posing some risk and opportunity depending on what happens to the price of fuel over the coming years. Here the risk is the price of the fuel. Thus, there is an event that affect the result of auto manufacturer gets. So, we have simplified the possible event outcomes into three categories. The first one is gas price increases, then gas price fluctuate up and down. The third one is the gas price decreases. Note that the probabilities of each outcome are identical for each decision choice, because the decision the auto manufacturer make does not affect the price of the gas. Under each possible outcome of the event, where whose probabilities we need to able to emanate, the auto manufacturer's decision choice will result in a different payoff shown on the extreme right. So, for example, 1200, 800 and so on. Note for example, that if the auto manufacturer chooses to develop only a hybrid model and the gas price decreases, the firm would expect loss of $200 million. Here we talk about the here. They go for only hybrid model. If the market in the market the gas price decreases, there will be a loss of $200 million. To evaluate each of these outcomes and make a decision, the auto manufacturer needs a decision rule. If our rule were to never pursue any alternative that might lose money, then rule out the hybrid only decision alternative, because the company says that we should not take any, we should not go for any loss. So, the company will not go for the second option of hybrid only vehicle. Another rule may be, if the decision makers at the auto manufacturer were optimist about the gas price, they might pursue whichever alternative provide the greatest opportunity for maximizing the payoff. So, which one is giving the greatest payoff? Then the auto manufacturer would choose a hybrid only option with a maximum payoff 1500 million from the when the gas price increases. However, we normally use a different rule called expected monetary value, that we shortly call EMV, because this maximizes our return over the indefinite future, that is long run average. The process of solving the decision tree is to work from right with the outcomes, that is the profit in each case, and multiply each outcome times the probability of the event resulting in the outcome called expected value of the outcome, and then adding up all the expected values for the event node decision choice combinations. So, what we have to do? We have to multiply this expect the monetary value with corresponding probability, then we have to add it. So, that will be your expected monetary value for that decision alternative. For example, the expected monetary value for the event node 2 here would be 0.5 multiplied by 1200 plus 0.3 multiplied by 600 plus 0.2 multiplied by 300. So, we are getting 840, which we write on the tree next to event. Similarly, we have done here 800, similarly here 650. When we have done this with all of the event nodes for the decision, we compare them and then double strike the lesser valued decision choices. So, when we compare these three, so 840 is there, 800 is there, 650 is there. So, whichever is smaller we are striking it off, so that we are not going to that path. That means that is not the good choices, and choose the best alternative choice for that decision rule, in this case developing gas only model. So, the here highest EMV is expected monetary value is for the first option, that is a gas only model. So, this is our the best alternative. Now, we will talk about a very popular way of analyzing the risk, that is called simulation. The simulation combined with the sensitivity analysis is also useful for evaluating project while they are still at the conceptual stage. So, before launching the product, it has happened for Chandrayaan-3 also. So, before the soft landing of Chandrayaan-3, they have done so many simulations in the earth by considering all the moon conditions. The same way for each project, when the project is at the conceptual stage, we can do the simulation, we can see the for different scenario how the project outcome will be. So, I have taken a sample, a problem for the simulation, that is a Monte-Carlo simulation. So, we are going to discuss about risk analysis for launching a new product. Assume that the company is launching a new product, we want to know the probability of the success, or what is the risk, what is the probability of failure of that new product. So, the product name is a portable printer. Assuming that the selling price of that portable printer is $249 per unit, and there are cost, administrative cost $400,000 and advertising cost $600,000. And most important thing is the simulation will have input that is probabilistic in nature. So, for example, labor cost $45 per unit, but that is it is not the fixed amount, it may change. Similarly, the part cost is a material cost $90 per unit, that also not fixed, it may change. And the demand 1500 units, but it is not fixed, it may change. So, we have 3 probabilistic input and we have the selling price and administrative cost for the new portable printer. So, in this problem first we have to find out the profit. So, what is the profit? The profit is selling price, that is a $249. Then we have to subtract labor cost and part cost, then that whole value has to be multiplied by demand. So, what will happen when you 249 minus labor cost minus part cost, so we will get a profit per unit. When you multiply by demand, so we will get overall profit. Then we have to subtract the fixed cost, that is advertisement cost and the overhead cost. How much it was? I will go back. You see here administrative cost, advertising cost. So, administrative cost is $400, advertising cost is $600, that we have subtracted. So, this is the function of profit. So, what is the profit function? 249 minus C1, that is called labor cost, minus C2, that is a part cost, multiplied by X, demand, minus advertisement cost and the administrative cost. Here there are 3 variables which are probabilistic in nature. One is C1, C2 and X. Here X we consider only the first year demand, because we are going to launch the product. So, we may not know the historical demand, we are assuming that the demand will be this much X. Now, we will consider all probabilistic input. The first probabilistic input is direct labor cost. We may not know what exactly the labor cost is going to be. For example, during COVID time the labor cost was very high, now it become very normal. So, similarly, there is a probability of the labor cost. For example, there is a 10% chance that the direct labor cost per unit will be $43. There is a 20% chance the direct labor cost per unit will be $44. There is a 40% chance the direct cost per unit, that is labor cost, will be $45. Like this, possible cost and corresponding probabilities is given. This is the first input. The second input is the part cost. Here part cost is material cost for manufacturing that portable printer. So, here the part cost follow uniform distribution. Previously the labor cost followed empirical distribution, but the part cost follow uniform distribution. So, what is the characteristics of that uniform distribution? The minimum is 80, maximum is 100. This is the second input. The third input is the first year demand. So, what is the assumption here is the demand is going to follow normal distribution, the mean is going to be 15,000 here and the standard deviation is going to be 4,500. These are my assumptions. Now, by considering these 3 probabilistic input, we are going to find out what is the risk of launching this product. Here risk in the sense, what are the chances for loss. In the Monte-Carlo simulation, if there is an empirical distribution, the first step is we have to construct a table. So, that will cover, say, direct labor cost is given and the probability is given, then we found the cumulative probability. So, we are going to find out interval for random numbers. How we are done? So, 0 to 0.1, then 0.1 to 0.3, because this will be your right side limit, then 0.3 to 0.7, then 0.7 to 0.9, then 0.9 to 1. So, what we have to do? We have to construct an interval for random numbers. If you are using a random number table randomly, or if you can use your calculator also, how to find out the direct labor cost randomly per unit. So, you have to choose the random number. For example, you are using a calculator. You say the random number is say 0.6, say random number is 0.6. So, we have to see where this 0.6 comes. So, here the 0.6 comes in this interval. So, the corresponding direct labor cost per unit is $45 has to be considered. Here I have some random numbers. For example, the random number is 0.91. So, we have to look at this table, we see where there is a 0.91. So, here there is a 0.91. So, the direct labor cost will be $47 here. You generate another random number 0.28. So, we have to look at the table where there 0.28 will be here. So, it will be corresponding direct labor cost will be 44. So, like that I have done 10 trial, then I have looked that where this random number appears in the table, then I have picked corresponding direct labor cost. So, this value can be used as a input for different iteration of the simulation. The second one is part cost. As I told you, the part cost follow uniform distribution. So, each trial in the simulation also requires value of the part cost and the first year demand. Let us now turn the issue of generating value for the part cost. The probability distribution for the cost of the part per unit is the uniform distribution as shown in this figure. Now, we have to generate different part cost that should follow uniform distribution. Because this random variable has different probability distribution than the direct labor cost, we use random numbers in a slightly different way to generate values for the part cost. With a uniform probability distribution, the following relationship between the random number and the associated value of the part cost is used. What is that relationship? The part cost is A plus R multiplied by B minus A. What is the A here? A is the smallest value of the part cost, B is the largest value of the part cost, and R is the random number between 0 and 1. What we do? So, suppose if you generate a random number from the table, that will be many times it will be 0 to 1, but we want random number. When you look at the table, we want a random number between 80 and 100, okay, because it has come from this table. So, the lower limit of this uniform distribution is 80, upper limit is 100, but if you use calculator, you are getting random number between 0 and 1, but you want random number between 80 and 100. For this, to convert a random number between 0 and 1 to 80 and 100, we have to use this formula A plus R into B minus A. This is called pseudo random numbers. What we are doing, why we are using this formula? We are converting random number which are generated from the calculator, and later we convert into the uniform distribution. That conversion is done by using this formula. Here A is your 80, lower limit of that random number, plus R is what value you will get from the calculator, then multiplied by B minus A, 100 minus 80. So, this formula should be used for converting pseudo random number which follow uniform distribution. If it is some other distribution, there will be a different formula. Okay. Here, since the part cost follow uniform distribution, you have to follow this formula. The third input variable is demand, but now we have to generate the demand that should follow normal distribution. That mean should be 15,000 and standard deviation should be 4,500. So, for this purpose, I am going to use the Excel function to generate this random numbers which follow normal distribution whose mean is 1500 and standard deviation is 4500. So, for that purpose Excel has the standard formula. So, if you use norm INV, normal distribution inverse, random, this number what you are generating, then the mean and the standard deviation. So, when you supply this, you will get this type of formula. If you in the Excel, if you use this one, you will get a random number which follow normal distribution by considering these two parameters. When you drag it, you will get as many number of random numbers which follow normal distribution. Now, I will go back to the Excel. I will explain how I have done this Monte-Carlo simulation using Excel, then I will come back to the result. Dear students, in the Monte-Carlo simulation, selling price is given $249 administrative cost is given $400,000, advertising cost is given $600,000, and there are 3 input direct labor cost which follow empirical distribution. We wrote that the probability interval, the probability lower limit and upper limit and direct labor cost when it is 43. If it is 44, we have given probability lower limit and upper limit, and we have done it for all other value of different labor cost. And here I have taken part cost that follow uniform distribution, lower limit is 80, upper limit is 100, and the first year demand, the mean is 15,000, standard deviation is 4,500. By using this input, I am going to do a Monte-Carlo simulation. So, the first one is labor cost. So, here the labor cost I am going to use a VLOOKUP function. So, equal to VLOOKUP function, then rand, then we have to select that table, that is from A10 to C14, then comma, you see 3, that is the value in the third column will be chosen. So, what is how this VLOOKUP function is working? Randomly we generate the number is traced in the table, in the probability table. Suppose the number is say 0.35. So, 0.35 is comes under interval 0.3 and 0.7, and the corresponding value is 45. That 45 is in the third column, that is why number 3 is written. So, that value is picked here. So, see this 45. So, what you can do, if you press F9, this value will change. You see that sometime 46, sometime 43. So, this is the way to generate the labor cost. The next one is the part cost. The formula for the part cost is the lower limit of that uniform distribution, that is given in E8. E8 is 80 plus random number, then multiplied by upper limit minus lower limit, that is E9 minus E8. Remember, here I have given the dollar sign because I have freezed it because I am going to drag it. So, this is the way to generate the part cost. Here also, for if you keep on press F9, please note this column C where the 81 will change when I keep on press F9. See, sometime 83, sometime 96, sometime 93 and so on. The third column, the third input is demand. So, here I am going to use norm.inv function rand, then I have to specify what is the mean and what is the standard deviation. So, here I got 9495. So, when you keep on press F9, see that I am getting, see that now I got 15,667, now I got 21,243. Now, I have randomly generated 3 input. Now, I am going to use the profit function to find the probability. You remember, in my presentation I am showing the profit function, that is a selling price that I have given in C3, selling price is in C3, that is a $249 minus labor cost that is there in B21 minus part cost that is in C21, then I have to multiply by demand, multiply by D21. So, I will get overall revenue minus there are 2 costs is there, one cost is there at C4, another cost in C5, 400,000 and 600,000, that also I am subtracting. So, in the last column I am getting the profit. So, for the trial one my profit is 13,63,968. So, I can drag it up to as many number of iteration. So, I have done how many trial I have done it? I have done it 500 trial I think, yeah I have done 500 trial. So, what I have done here? Randomly generated the labor cost, part cost and demand, then I have used profit function. So, the last column E is the profit function, right, here I am getting. So, I got some statistics, mean profit is 7,12,259, standard deviation is given, minimum profit because I have there is a min function, then maximum profit I given there is a max function. Here the number of loss, it is more important. So, here to find the number of loss I have used a COUNTIF function. So, equal to COUNTIF, in that profit column E21 to E520, wherever there is a negative profit, that I have considered as the loss. For example, here the number of loss is 39. So, if I press F9, you see the 39 will change, see 33, it is 43, it is 41, it is 46. So, that is the number of loss. From this, what I am going to do, the probability of loss. So, probability loss is number of losses upon total number of iteration. So, here total number of iteration is trial is 500. So, number of losses upon 500. So, this, for example, here at present there is a 9% chance that the new product will enter into the lossing situation. So, when we keep on press F9, please observe only the profit loss column. So, you see that sometimes 7% loss, sometimes 8% loss, sometimes 6% loss. You can observe that the loss always below 10%. So, what we conclude from here is, if you launch this new portable printer, there is a 10% chance that this may fail in the market. So, this is the conclusion of this Monte-Carlo simulation. Now, I brought the summary statistics. So, I got the mean profit, standard deviation, minimum profit, maximum profit, number of losses. So, the probability loss is 5.6%. So, this is the way to do a Monte-Carlo simulation to assess the risk of launching a new product. Next, we will discuss about sensitivity analysis. Here the sensitivity analysis is, for example, we consider 3 input: labor cost, part cost and the demand. We assumed that labor cost followed empirical distribution, part cost followed uniform distribution and the demand followed normal distribution. Suppose if the distribution changes, what will be the impact on the risk? So, that can be done with the help of sensitivity analysis. So, sensitivity analysis or what if analysis can be used for both quantitative models, it most common use, but also in qualitative models. The process is to go back into the model and change one of the parameter or variables and see what the impact is in the final result. For example, we consider the mean of the demand distribution is 15,000. Suppose if it is 20,000, what will happen? So, that change in parameter and corresponding impact on the risk can be done with the help of the sensitivity analysis. So, in this way we can see that what will have a major effect on the result, and thus our decision about what to do and what will not affect or will have a trivial effect on the result. So, we do not need to worry about that. So, these kind of conditions can be assessed when we do sensitivity analysis, whether impact is going to be severe, whether there is no trivial impact. So, these kind of inferences can be obtained with the help of this sensitivity analysis. But in the Monte-Carlo simulation I did not do the sensitivity analysis. You can do by changing different parameters and we can see what is the impact of that. For example, in the failure mode effect analysis, we might see what a change in the severity of threat might do, or in the decision tree how the change in the outcome will change the result, or in the simulation what changing a distribution might do our profit. That can be done with the help of sensitivity analysis. We can also consider what adding a new threat might do to our analysis, or adding a new branch in the decision tree or inflation in our simulation. One weakness of sensitivity analysis is that a single change in the environment does not usually happen. Instead, many variables or parameters commonly change at the same time, which is harder to check and determine how it might affect our decision. As I told you, sensitivity analysis is done by changing one parameter at a time, but many times that may not help. So, what we can do, simultaneously we have to change different parameters, then we can see overall impact. That is very difficult to do with the sensitivity analysis. There is also a form of sensitivity analysis where the impact of alternative development or scenarios in the completion of the project are predicted. For example, What would be the impact on the success of the project if the project manager left the organization? If a major contractor suffered a strike by a labor union, if an important new technology did not perform as expected, if a competitor beat us to market. So, these kind of scenario analysis also can be done by doing an advanced simulation analysis for assessing the project risk. Once alternative scenarios are identified, they can be analyzed with the tools discussed earlier, including failure mode effect analysis, decision tree, Monte-Carlo simulation, and contingency plan should be developed for scenarios where the predicted impact is particularly severe. So, in this lecture, dear students, I have discussed about various quantitative techniques for analyzing the project risk. I have discussed 3 quantitative techniques. One is failure mode and effect analysis, second decision tree analysis, third one with the help of Excel. I have explained how to use Excel for doing Monte-Carlo simulation. Then finally, I have explained the importance of sensitivity analysis. Thank you.